In preparing for this lesson, I came up with an incredible number of regular expression examples, some of which are quite evil. Just like any topic in mathematics, seeing examples goes a long way to understanding the theory. And so what we're going to do now is do some examples of regular expressions. Watching this before you watch the intro to regular expressions is probably not a good idea, because we're going to start off right with some regular expressions. So first of all, we're going to look at the Latin alphabet. That's going to be our alphabet. Okay, and I'm going to give you a regular expression. Now the regular expression I'm going to give you is just EFH. There's my regular expression. Now, notice there are no characters, no parentheses, no stars, no daggers, nothing, EFH. What exactly does this regular expression evaluate out to be? In other words, what is the regular set that is generated by this regular expression? And so you have the Latin alphabet. Let's just call this A is equal to the Latin alphabet. And remember, A star is the list of every possible finite string you can generate from the characters inside of this Latin alphabet. And whenever you look at a regular expression, it's going to create a subset called the regular set that is a subset of this A star. And so what is the regular set that is generated by EFH? Guess what? It is just the set EFH. All right. Now, let's start adding some characters to this. For example, what if I did E star, F star, H star? What would that generate? Now remember, the star says every possible string, including the empty string, that lambda. Remember, the lambda was the empty string, the string of length 0. So the star is going to make it so that we're going to create every string from what it is a star of, including the empty string. So there could be anywhere from no to a bunch of E's, anywhere from no F's to a bunch of F's, anywhere from no H's to a bunch of H's. So this could in fact include the empty string. I could have an empty string concatenated with an empty string, concatenated with an empty string, which gives you the empty string. It could be just a E. Could be 2 E's, could be a whole bunch of E's, right? Could be 1 F, 2 F's, a bunch of F's. Same for the H's. All right. Two that is if for these where there's just a single character, that would mean that the other two regular expressions, so this F star and H star, if they were both empty strings, then you'd have any number of E's. If E star and H star both selected the empty string, then you'd have any number of F's, and so on. But the key is what we can have is any number of E's followed by any number of F's followed by any number of H's. All right, they're always going to be in that order because there's no mechanism in this regular expression to swap things around. Now, what if we tried something slightly different? What if we went with a regular expression like E F star H, okay? Now, in this case, the empty string is not one of the options because it has to have, note, I don't have any parentheses grouping things together for this star to be applied to. So there has to be at least one E and there has to be at least one H. So the smallest string we can come up with is EH. And then you just start adding F's. All right, and so E, F, all the way, and we keep going, right? And so the idea is that we can have any string where we have an order E, F, H, where there's exactly one E, exactly one H, and any number of F's in between them. What about EF star? E and F are in parentheses, star H. Well, in this case, what the star is being applied to is the concatenated string EF, which means that I could have no EFs, I could have one EF, two EFs, three EFs, and it would be repeated. They'd have to stay in that order. Regardless of how many EFs we include, there has to be a single H terminating the string. So this would be just H, where EF is the empty string, and EF star, excuse me, is the empty string. Then EFH, EFEFH, and so on. All right? Kind of getting the idea of how these stars and so forth work. What about E or FH? Now, this little v, this little tiny v, is representing, remember, the OR. And so I have E or F, then concatenated with a single H that comes at the end. So it turns out there are only two strings here. We have EH or FH. Those are the only two strings that are supported by that regular expression. That is our regular set right there. And if we went a little further and said E or F or H and brought the H into that OR expression, what you're looking at is the regular set E or F or H. Kind of like exactly the way we said it, right? And so E or F or H generates that regular set. But what if we make this even fancier? How about E or F or H star? Okay, now this is where things get a little bit complicated. And in fact, you know, what we did was we said, I've got this A star. If A is the Latin alphabet, A star is every possible string you can come up with for that particular alphabet. Now, this really is the same sort of thing, except what we've done is we've reduced our alphabet down to E, F, and H. And so really what you've got is, of course, since we have the star applied to parentheses, it includes the empty string. So, you know, the star says all the possible combinations, including the empty string, of everything inside of those parentheses right there. And then what you're doing is you're saying any combination of this regular expression. Well, this regular expression generates this set right here. And so when you look at this set, what you can do is you just pick one of them, and you can concatenate it with another one of them, which you can concatenate with another one of them. And so you can get basically any string that can be created from those three letters. So E, 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 H, F, E, E, H, F, H, E, E. I mean, there's all, and the order doesn't matter. You can just go back to this expression, pick another one, concatenate it. Go back to this expression, concatenate it with another, pick another one, concatenate it, and so forth. So that gives you an idea of kind of looking at just starting with a really simple 3 characters as our part of this regular expression, but how you can add parentheses, ors, asterisks, and so forth in order to create more complex regular sets. So what I'm going to do now is look at the binary alphabet, which, remember, is just 0 and 1. And we're going to create a number of regular expressions using just that binary alphabet based on some description that I'm using to create some, you know, I want to have a regular expression that does this. So let's try something really simple. What I want to do is come up with a regular expression for, let's say, how about 0, 1, 1, 1 or 1, 1, 1, 1. All right. Now, real quick, what I'm saying is that I need a regular expression that is going to pull from this binary alphabet. And let's just say that we're setting B equal to this binary alphabet. So our set B star is every possible combination of ones and zeros into a string that we can come up with, finite length, including the empty string. And what I want to do is come up with a regular expression that will pull just these two out of that combination of everything, right? Well, I've already really kind of set it up here. This is just 0, 1, 1, 1 or 1, 1, 1, 1, right? Is that the only way we could write this? Well, not really. If you look at this, we actually have two strings that both of them end in 3 ones. So this actually could be written as 0 or 1 concatenated with 3 ones. Okay, all right. And so both of these regular expressions will pull the regular set of 0, 1, 1, 1 or 1, 1, 1, 1 out of B star. Now, let's take a look at this guy and see, now what I'm doing is I'm changing the problem. Let's take this guy, we'll do 0 or 1, followed by 1, 1, 1, 1, and we'll put an asterisk, just 3 ones, I think I said 4, put an asterisk outside the parentheses for 0 or 1. What does this do for us? Well, remember that whenever you have this or with the asterisk outside the parentheses, what you're saying is every possible string, finite string, including the empty string, made from ones and zeros. All right? So this 0v1, this 0 or 1, in parentheses with an asterisk, what that is saying is any possible combination of ones and zeros. And you can take any possible combination of ones and zeros, concatenate it with 1, 1, 1. You're basically saying this is any binary string ending in 1, 1, 1. So let's continue to stick with our binary alphabet. And we're going to come up with a couple of more requirements. How about a regular expression for strings that contain, let's see, how about exactly 1, 1? All right, what would we need? Well, our string should have a 1, right? And then before it or after it need to be some number of zeros. That 1 may be at the beginning, so what we need here is an empty string or a single 0 or 2 zeros or 3 zeros or so on and so forth. And similarly, we want the same thing after it. We want the empty string, 1 0, 2 zeros, 3 zeros, and so forth. So what can we put? Is there a regular expression that represents this? Well, of course there is. It's just 0 star. So if we put a 0 star here and a 0 star here, that is going to satisfy the regular expression for strings that contain exactly 1, 1. So it could be the first one if we have an empty string here. It could if we have an empty string for this first position, and for this last position, if we have an empty string, the 1 could be the last one. Or there could be any number of zeros padding it on either side. Now, how about if we did something like any string that starts with a 1. Now, I'm not saying that there's only 1 1. There can be any number of 1s. What I'm saying is I want to make sure that the first digit is a 1. So, for example, something that would satisfy this would be 1 0 1 1 1 0 0 1. Also 1 0 0 0 would satisfy it, or 1 1 1 0 0 0 1 would satisfy it. Any of these would satisfy it. And so what we want is we can define this first bit. That first bit, it just needs to be a 1. But we need to concatenate it with any pattern of 1s and zeros. Any pattern, including the empty set, because it could just be it's a single digit, a single bit, 1. Well, how would we do that? Well, remember from before that 0 or 1 star represents any possible sequence of 1s and zeros. It'll represent anything. Just keep picking one or the other and keep concatenating them together until you get whatever string it is that you're looking for. So starts with a 1. And heck, we could do ends with a 1 too, right? That would just simply be any string of binary from the binary alphabet followed by a 1. Good. Let's make some room. Now, what if we wanted to have one that starts with 0 and ends with a 1. Well, that means we have 0 followed by any binary string ended by a 1. And in fact, this any binary string could just be an empty string because 0, 1 satisfies this condition. Well, what do you put in here? Well, once again, 0 or 1 star. That will give us any possible pattern of 1s and 0s. Let's see, how about a string containing at least 1, 1 and 1, 0 in any order? That one's a little bit more tricky. Let's see. How about this one? This one's going to be tricky. What we're going to have is could be some string of any length, followed by a 1, followed by a string of any length, followed by a 0, followed by a string of any length, or, and there's that or again, right? I mean, if we say the word or, there's going to be an or in our regular expression, right? So we could have or, any string, any binary string, followed by a 0, followed by a 1, followed by any string, right? So it's either of these guys. Now, what I would like to suggest, because you can probably do this, right? So here's any string. All we want to do is substitute that into each one of these blanks here, and you would get 0v1 star 1, 0v1 star 0, 0v1, right? Star, and then put extra parentheses to group this one, and then simply say or, and then do exactly the same thing. 0v1 star, except we're going to have a 0 come first. 0v1 star 1, and then 0v1 star, and there you go. I said this could be pretty ugly. That looks like a pretty evil expression. But you know, we could change this around a little bit. In fact, let's try this a slightly different way. Notice that we've got this portion starting with a 0v1 star. This one also starts with a 0v1. And this one ends with a 0v1 star. And this one ends with a 0v1 star. So what if we tried something like this, and in fact defining this a slightly different way? I could say any binary string followed by a 1 with any string 0, or 0 with any string followed by a 1, and then followed by any string. And so what you've got is we've got any binary string, any binary string. And in between them, I either have a string that starts with a 1 and ends with a 0, or a string that starts with a 0 and ends with a 1. All right? Now, what I want to do, let's do this. Writing this one down should be pretty easy. So this would be 0v1 star, right? Concatenated with 1, 0v1 star, 0. Or, and that comes from this, so this 0v1 star is for this piece right here. This 1, I'm sorry, I'm sort of standing in front of this. This is 1, 0v star 0 is this piece, that piece, and then this piece would be 0, 0v1 star 1, and then 0v1 star. And all I've done is just simply, these 0v1 stars are going in these blanks where I said any binary string could go. But there's something else that I want you to notice here. And that something else I want you to notice is that if I've got a 1, to get to a 0, at some point, either this binary string right here, even if it's a whole bunch of 1s, if it's a whole bunch of 1s, it'll eventually get to a 0. And so let's assume, we got a whole bunch of 1s here, and it gets to a 0. Notice that right here, I have a 1, 0. Now, it could also be such that this string right here could actually just be a whole bunch of zeros, in which case I have a 1, 0 here. So this string at some point is going to have the string, concatenated string 1, 0. Let me try that again. Hopefully it'll make more sense if I explain it again with this second situation. So here I could have 0, and then this any string that's here could just be a whole bunch of zeros followed by a 1. Or it could actually be a whole bunch of zeros, just a whole bunch of zeros. And so in the string that's made up by that whole expression right there, I'm eventually going to get a pattern 0, 1. Now, I could actually have the pattern that's in between that 0 and 1. It could be just 0, 0, 1, 0, 1, something like that. Notice that I also, again, have the pattern 0, 1. And heck, I could also have it so that that binary pattern that gets inserted here is all 1s, in which case, once again, I have a 0 and a 1. So what I could do is take all the stuff that doesn't become part of this and strip it out and include it in this string, and all the bits in here that's not part of the 1, 0 and strip it out and include it in this bit. And what I could do is I could say, let's try this slightly differently. I could say that this is any binary pattern, right? Followed by a 1, 0 or a 0, 1 followed by any binary pattern. Wow. That's a lot of ways to come up with representing a string containing at least 1, 1 and 1, 0 in any order. All right, because, for example, let's just say, and this is getting kind of long, but I want to cover this. I could have this string. It contains at least 1, 0, 1, 1, right? 1, 1. Does this regular expression fit this? Well, what you could do is you see the 0, 1 here. That is right here. And this string could be made by this expression, and the empty string could be made by that expression. Try another one. How about 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, okay? This string right here, well, goodness, there's all sorts of ways it'll match this regular expression. I could have this first bit right here representing the empty string. The 1, 0 is that bit right there, and then the rest of the string, this piece right here, could be generated by that expression, that regular expression. Or I could have this regular expression generating a 1, and then we have 0, 1, there's the 0, 1, and then the rest of the string being generated by that expression. So there are a number of ways that this particular requirement or this particular regular set could be generated by a regular expression. Now, to continue our discussion about regular expression examples, I'm going to talk about a real topic, subnet masks. Now, I know that I keep introducing these topics that seem like they're a pretty complicated topic. Don't worry, we're not asking you to understand networking principles. All I'm saying is that there is such a thing as a subnet mask which relies on the binary alphabet in order to identify where to route messages to. Just giving you an idea that this stuff happens out in the real world. Now, a subnet mask typically is a bunch of 1s followed by a bunch of 0s. Now, I'm not going to specifically address subnet masks because depending on the application, a subnet mask has a fixed number of bits. But what I'm going to say is I want the length of this subnet mask to be greater than or equal to 2. So it has to have at least 2 binary characters, either a 0 or a 1. And that all 1s are followed by all 0s. In other words, the binary mask is always going to look like 1s to the left and 0s to the right. There will be no mixing of 1s and 0s. So just to give you an idea, we've got 1, 1, 1 followed by 1, 1, so all 1s, right? And then as we go, maybe if we've got a single 0, it's got to appear on the rightmost position. If we have 2 zeros, they have to be in the rightmost position. 3 zeros have to be in the rightmost position. If we only have 2 ones, they have to be in the leftmost position. 1 1, it has to be in the leftmost position, and no ones. The whole string is filled up by all zeros. So this gives you an idea of what we're looking at when we're talking about subnet masks. Now, granted, I've shown here examples that have at least 6 digits, but remember, we could have just 2 digits. I'll get to that in a minute. Let's take a look at defining a regular expression for all of these in the middle, everything except for the all ones case and the all zeros case. What is that going to look like? Well, what you've got is at least 1 1, right? So all of these begin with 1 1. And then at the end, you have a single 0, right? And in the middle, you have some number of 1s followed by some number of zeros. Well, some number of 1s could be 0 1s, is 1 star, right? And some number of zeros could be 0 zeros, is 0 star. And so we've got this definition here that shows how to do this middle group. It's a 1 followed by some number of 1s, followed by some number of zeros, followed by exactly 1 0. So this, another way of saying this is it must start with a 1, it must end with 0, and in between you've got 1s followed by zeros. All right. Now, if you remember our nomenclature, you also realize that this is really just 1 dagger, 0 dagger, which represents the idea of at least 1 1 followed by at least 1 0. All right. There you go. That's the middle bit. Now, how do you do the top and the bottom? Well, the top and the bottom, the top one has to be at least 2 1s. Remember that we have to have a length of at least 2. So it must be at least 2 1s followed by any number of 1s, right? And this is the same thing as 1 1 dagger. So 1 1 star or 1 1 dagger. Same thing for the all zeros case. Must be at least 2 zeros followed by any number of zeros, which is defined by 0 star, which is the same thing as 0 0 dagger. Now, what we are doing to define this idea of a subnet mask is it's this regular expression followed by this regular expression, well, excuse me, this regular expression or this regular expression or this regular expression. So what you get is 1 1 dagger or 1 dagger 0 dagger or 0 0 dagger. And there you go. There's a regular expression that defines a subnet mask. Now, something that I want you to see in this expression, or excuse me, in these examples, because what we're going to do is we're going to look at another way of defining this, is that, remember, they have to be at least 2 bits. And so if I draw a line right here, you'll see that regardless of how many digits our example has, there are only 3 ways it can start. It can either start with a 1 1, it can start with a 1 0, or it can start with a 0 0. And so those are the only 3 ways that we can start this string. If it starts with a 1 1, so in this case what we're looking at is all of these cases where it begins with 1 1. If it begins with 1 1, what can it be followed by? Well, it's followed by some amount of 1s or followed by some amount of zeros. So we could have all 1s or all the way down to no 1s. And in the case of the zeros, it can be no zeros all the way up to all zeros. Well, these guys will just be defined by 1 1 followed by some number of 1s, which could be the empty set, followed by some number of zeros, which could also be the empty set. So worse, if we've got empty sets for both of these guys, it'll be just 1 1. If we have some number of 1s or zeros in each one of these sets, it'll be all 1s, then followed by a bunch of zeros. So these cases right here are defined by that expression, which could also, once again, be 1 1 dagger 0 star. All right. Now, this guy right here, how do we define this? Well, this guy is 1 0 followed by some number of zeros, right? Which is the same thing as 1 0 dagger. And then this bottom one here is 0 0 0 star, right? which is the same thing as 0, 0 dagger. So we have another way of expressing the regular expression for this subnet mask thing. It could be 1, 1 plus 0 star, or 1, 0 star, or, excuse me, 1, 0 dagger, sorry about that, or 0, 0 dagger. And so we have two regular expressions which basically define the same thing. Let's do another example. I'm going to talk about something called UTF-8, and a portion of which is the same as ASCII, but what specifically we're looking at is decimal digits. Now, when it comes to representing characters on the screen, understand that the number 1 is not equal to the character 1. Those are two different things. This is a value, an integer. This is a pattern of 1s and 0s, a binary pattern of 1s and 0s that represents the character 1 that's going to be displayed to the screen. So this is a value, this is a character, two different things. Now, when we're looking at ASCII or UTF-8, they both represent this character 1 the same way. The character 1 is represented with 0011 0001. All right? That's how this pattern of 1s and 0s, when stored in memory, represents the character 1. And in fact, we'll go above that. The character 0 is represented with 0011 0000. And then as we go down, 2 is 0011 0010. 3 is 0011 0011. And we keep going down until we get to 7. The character 7 is 0011 0111. The character 8 is 0011 1000. Character 9 is 0011 1001. Now, the way this works, what we want to do is come up with a regular expression that allows us to look at 8 bits and determine whether or not it is a decimal character. Now notice that all of them start with 0011. So that's going to be the beginning of our regular expression. That's going to be how we start off our regular expression. But the question is what regular expression do we concatenate it with to represent these? Now I could have some huge OR statement, right? I could have 0000 or 0001 or 0010 and so forth until we get down to 1001. That's okay, but there might be an easier way to do this. For example, all of these that start with 0, we could then group them together so that we're then looking at these patterns of 1s and 0s, which, by the way, there'll be 3 digits for 0 through 7. There'll be 3 digits that will go through every possible combination of 1s and 0s for those 3 digits. Then we also have 8 and 9, which have a 1 in this position, followed by 2 zeros, followed by either a 0 or a 1. Let's do these two guys first, okay? Let's go ahead and figure out what gets concatenated to the 0011 in order to make an 8 or a 9. Well, it's always 1, 0, 0, followed by 0 or 1, right? And so this concatenated with this identifies either the 8 or the 9. These guys are going to be a little tougher. Those are going to be a little tougher to identify a regular expression for. For this piece right here, what you're going to be looking at is a 0, followed by a 0 or a 1, followed by a 0 or a 1, followed by a 0 or a 1. So these are the 3 digits at the end. It's these 3 bits right here. So those, and so forth. And by saying 0 or 1, 0 or 1, 0 or 1, what we're looking at is those last 3 digits. Now I can't use an asterisk because remember, if I used an asterisk, it would give me any length. And I don't want any length, I want exactly 3 characters. And at this point in our understanding of regular expressions, all we know is to just simply write out these as 3 OR statements. So what does our regular expression for decimal digits in ASCII look like? Well, they always start with 0011. And then it is either 0 concatenated with 0 or 1, concatenated with 0 or 1, concatenated with 0 or 1. So this bit right here identifies this group right here. And then, let's see, then ORed with what defines an 8 or a 9. And that's 1, 0, 0, 0 or 1. And I think I got that right. Probably the number of parentheses. We probably ought to put parenthesis there. We need to put the parenthesis here so this doesn't become this expression ORed with just the 1, 1. Those all have to be kept together. There you go. A definition for how to detect an ASCII decimal digit. And by the way, whenever you look, if you do something like search on ASCII table, you will come up with tables that show you how every single character on the keyboard can be represented. And you can create regular expressions to search for capital letters or lowercase letters or punctuation marks, any of that stuff. Now, one last one, and I know I'm asking a lot from you, but I really want to get through this last example too. One of the basic, really primitive methods of error checking is something called parity. Now, what parity is if you look at a binary string, you're looking at the pattern of ones and zeros that is created from this alphabet, right? Parity counts the number of ones in binary, for binary parity. And if you have an even number of ones, then it has even parity. If you have an odd number of ones, then it's odd parity. Remember, once again, these are topics that are beyond what we're going to look at with this class, but I do want to show you the application we're aiming for. And so what I've got is this idea of even parity. I want to make sure that the number of ones in the binary string, and once again, this is a finite binary string, is even. All right. So that means I have 0 ones or 2 ones or 4 ones or 6 ones or 8 ones. Got to be an even number. Well, let's start with exactly 2 ones. Now, how would we define this? Well, it's going to have exactly 2 ones. And then before the first one and after the last one and in between, we're going to have some number of zeros, right? Well, some number of zeros is just simply 0 star. So we have 0 star. So 0 star 1, 0 star 1, 0 star 1. This will give us the regular expression for exactly 2 ones. Well, what does exactly 4 ones look like? What does exactly 4 ones look like? Well, 4 ones is going to give us 0 star 1, 0 star 1, 0 star 1, 0 star 1, 0 star. All right. And so we've got 1, 2, 3, 4 ones with some variable amount of zeros in between those two. All right. And 6 ones, you just add another one of these after. And in fact, what I'm looking at, I probably did a quick jump, 0 star 1, 0 star 1, 0 star, that's exactly 2 ones. And if I concatenate it with a string 0 star 1, 0 star 1, 0 star, then this is also a string with exactly 2 ones, which is really a string with 4 ones. I take away these parentheses, and if you look right here, this 0 star, 0 star, guess what? That's just a 0 star, right? So that gives us this pattern, that regular expression right there. Now, the way we could look at this is that it looks like if we have some amount of zeros followed by a 1, 0 star, 1, 0 star, and then we put a star here in order to make it so that we take that string in there and we can duplicate it. Well, not duplicate it, but we can make a copy of a string. Copy is also the wrong word. We can have a string with exactly 2 ones followed by a string with exactly 2 ones followed by a string by exactly 2 ones over and over again. This guy should give us the regular expression we're looking for. Now I took this 0 star outside of the parentheses. We could have done something like 0 star 1 0 star 1 0 star and put a star here. There's a problem with this though, because there's one case that this does not allow us to address, and that's the all zeros case. So if I had all zeros, there's no way to use this regular expression to represent, it cannot represent on the all zeros case, which is also an even parity, because there must be at least exactly 2 ones in this expression if we're going to have anything. It's either going to be the empty string, or if it's not the empty string, it's going to have at least an even number of ones in it. So this guy right here does allow us to have the all zeros case, because if this evaluates out to the empty string, then we've got this random number of zeros that we can put in there. Does it work for all ones case? For example, if I have 8 ones, which has even parity. Well, 8 ones, I could have no zeros, the empty string, and the empty string for this 0 star, and the empty string for this 0 star, and just have 2 ones, and then this star here allows me to duplicate it 4 times, which would give me 8 ones. So it does work for a string of all ones, works for a string of all zeros, works for any of the even parities that we're looking for. All right, I am so sorry. That was a huge, huge long lesson. But there's all sorts of examples that we've given to you in this lesson. We also got an opportunity to introduce subnet masks, ASCII decimal digits, even parity, all sorts of things. Just some great things that you will be using in your career as a computing professional.